Welcome back, students. Let's complete section 1 of this notebook. We are done with everything except one, and that is the subadditivity of the norm. Or it is alternatively called the triangle inequality. Excuse me. Now, how do we prove it? Well, we are working out with norms, so it's not surprising that we'll have to square both sides because, after all, the norm was defined using square root, and square root is difficult to handle, so if you square both sides and then take norm squared, it's a lot easier that way, so most of the proofs about norms start from squaring both sides. So we'll prove this like this. Yes? No. Something's wrong. Badly wrong. What did I do wrong? Well, I hope nobody fell for that because this is 3000 level course. In 1000 level course, of course, many students fall into this trap, but in 3000 level, I have higher expectation. So the left-hand side square is okay, this is single entity, but here we have addition, so we need complete square, not just square plus square. So this is what we have to prove. And once you establish that, if you simply take the square root of both sides, we're going to get this one, because both are positive, not negative quantities, so you don't really have to talk about plus or minus square root. Just square root is fine. Let's do it this way. And from here, you can put it into the definition of the norm, right? The norm squared, so it's scalar product of itself, and then work it out from there. Well, here we go. Here's the proof. First line, what do we have? We have scalar product of v plus w and v plus w, fine. Next, we fold it out. First, outside, inside, last. And then these two, outside and inside, are the same because of the symmetry. So we have 2 v dot w, and then scalar product of itself, the norm squared. Scalar product of itself, norm squared. Now, the key is the transition from here to there. I just highlighted it in red. Now, please note that this is greater than or equal to that. If so, then I can move from here to there using the what do you call the complete square formula. Yes, complete square formula. This formula, a plus b squared is equal to a squared plus 2ab plus b squared in elementary algebra. All these are real numbers now here, so it works out just fine. Over here we have some vectors, but here real numbers, so no problem there. The key is this red is greater than or equal to that red. Now, how do you set it up? As a matter of fact, I assigned this problem way back in module 2, week 2, but there we defined the scalar product or the dot product using angles at that time. So we could do this. So v dot w is same as norm of v times norm of w times cosine of theta, and let's see, cosine of theta is bounded by positive 1, greater than or equal to negative 1, but less than or equal to positive 1. So if I drop it, replace it into 1, then that will be an overestimation. You see, cosine of theta is less than or equal to 1. Replace cosine of theta with 1, then this is greater. But there's a bit of a problem with this approach. In week 2, it was okay because we are doing the scalar products with the angles there. After all, we are dealing with only, excuse me, wrong cell again. We are dealing with only this one. So yes, we had angles. But if we go outside those Euclidean geometry, then where's the angle? Let's open that example again. Where's the angle here? Doesn't make any sense. How about the angle over here? Doesn't make any sense. No, they don't. So we are not allowed to use angle, and we have to do something better. What do we have to do? One way to do that is to use this, which we call Cauchy-Schwarz inequality. So bypassing this one, please note that V dot W is even less than or equal to this absolute value of that, because absolute value makes everything non-negative, so it can increase or at worst stay the same. And then it can increase even further by taking the norms of V and W later. So you see, this red is less than or equal to that red because of this Cauchy-Schwarz inequality, and consequently the last line follows. So we don't have to do the angles if you use Cauchy-Schwarz inequality. Fold it out and then simplify, and from here to there directly using Cauchy-Schwarz inequality, and then from here complete square. Once you have that, taking the square root of both sides, we're going to get what we want. So everything boiled down to proving this, and for the rest of the video we're going to do that. Okay, alright. Here in this chapter, we're going to do this in two different ways. One is using the orthogonality, and that's something we are going to do in section 2, where we deal with a lot of orthogonality. The other method is something we are going to do now. We're going to be using the property of quadratic functions. Okay. So orthogonality example, that's going to show up here in section 2 because we have to use a lot of section 2 topic there. Orthogonal projection, orthogonal component, and those kind of things. But there's another way using the quadratic functions. Okay, all right. Okay, let's set up this problem like this. Out of nowhere, let's consider this function, f of t equals to tv minus w, scalar product of tv minus w. So this is scalar product of itself, so always greater than or equal to 0. Does it make sense? Scalar product of itself, so always greater than or equal to 0. And equality, if and only if we have the 0 vector. So always greater than or equal to 0, and equal to 0 if and only if we have 0 vector. tv minus w is equal to 0. And that's something we're going to come back and discuss in a moment. But for now, let's focus upon this. Always greater than or equal to 0. Is that clear to everybody? Okay, remember that. Always greater than or equal to 0. And then let's work out this foiling. Here, first, t squared times v dot v. Outside, t times v dot w. And inside, t times w dot v, so we get the second term. Make sense? Finally, last, w dot w minus minus plus, so we have plus w dot w. And v dot v, you can write it as norm squared. W dot w, we can write it as norm squared. and then this coefficient here is negative 2v dot w. And what we have a quadratic function a t squared plus bt plus c is always greater than or equal to 0. So we are in this kind of situation. Let me emphasize again, always greater than or equal to 0. That came from this factor, scalar product of itself, so always greater than or equal to 0. Equal to 0 if and only if we have 0 vectors there. And after foiling, we got in this form. And then this is at squared plus bt plus c is greater than or equal to 0 in that form. Okay. And then let's have just a little bit of digression. In order for this quadratic functions to be always positive, we should not be having any x-intercepts. Excuse me, we can have touching, but we cannot have two x-intercepts like this. So this is bad. Part of this curve goes below the x-axis. So for some t values, this f of t is negative, no good. This is barely okay because always greater than or equal to 0, and it is possible that equal to 0. And this, of course, is the best, always strictly greater than 0. So we have to consider these cases. When do we have these? Well, how do we get the x-intercepts? We have to set this thing equal to 0, or in terms of x, a x squared plus b x plus c is equal to 0 if and only if x is equals to negative 2b, negative b plus or minus, is plus or minus squared b squared minus 4ac over 2a. Does everybody recall this? The quadratic formula. And plus or minus square root will give you this and that. And if this quadratic, this part, the square root part is 0, then you're gonna get this. And if this is negative, then no real root, we're gonna get that. So we are looking at the inside of the square root less than or equal to 0, basically, because this expression, this quadratic expression, is always greater than or equal to 0. We should not be having this. It should be either this at worst or that. So the inside of the square root, b squared minus 4ac, has to be less than or equal to 0. And coming back to this, b squared minus 4ac, this squared, so 4v dot w squared, minus 4ac, 4 times a, c. And that's how we get this inequality. Let me show you the picture again. This is bad. We have to have either this or that. So b squared minus 4ac has to be less than or equal to 0, okay? And That's why we are getting that. Once you get here, that's easy. Flip this 4v squared w squared to the other side, we get this. And then divide by 4, we get that. And then take the square root, we get what we want. So the absolute value of v dot w is less than or equal to norm of v times norm of w, and that's precisely what we want. And this part is not really that necessary, so let me remove that. Okay. So from this quadratic expression, using the discriminant at all, we ended up proving it. So the absolute value of the scalar product is less than or equal to the product of norms. And at worst case, we have equal to 0 when we have 0 vectors. TV minus W is a 0 vector. And that's equivalent to W is equal to TV. W and T are parallel to each other. Same direction, so the angle is 0, or the opposite direction, the angle is 180 degrees. So same direction, then V dot W is also positive, and we have equality. And opposite direction, V dot W is negative, so if I take absolute value, then we have equality. So we completed. This is always true, and equality holds if and only if we have parallel vectors. Now, if you take that and apply that to the subadditivity, we get jump from here to there. This red is less than or equal to that red because of Cauchy-Schwarz inequality we just proved. Okay, so much for these two inequalities. Triangle inequality or subadditivity of the norm and Cauchy-Schwarz inequality. Both are, as a matter of fact, very, very important inequalities in analysis. Now here in linear algebra, important too, to a certain degree, but I don't know. In terms of proofs, I think producing these out of scratch will exceed the level that I'm thinking for this course. So you don't really have to be able to do that. But as for using these, yeah, you should be able to do that. Cauchy-Schwarz inequality, proving that out of nowhere is going to be a bit too much. But using Cauchy-Schwarz inequality to prove the subadditivity, set up like this and go from here to there, yes, that's within my expectations, so you should be able to do that. And of course, using the subadditivity to do something else, that too you should be able to do. As for Cauchy-Schwarz inequality, I don't know about that. Well, it was a difficult theorem, but we went through it, and I hope everybody understood it, and that's enough for us. Thanks.